So in the previous class, actually before we do this, so I have a certain pattern, okay? So every class, to try to maintain the continuity, I spend the first 10 minutes or so trying to review what we did in the previous class, so that the stage is set for the next class. Okay, there is some amount of continuity. So in the previous class, we started looking at the definition of these terms and why we use voltages and currents. There is a very specific reason. From an engineering point of view, from an analysis point of view, voltages and currents are much easier to work with. Okay, their effects and measurements are much easier. At some point of time, you have to go back to the physical quantities, and you will learn more about these in other courses, as I pointed out, in solid state devices and in electromagnetic field. Okay, but you will find that in a majority of these situations, it's much easier to just work with voltages and currents. We started off with the analogy between the case of a gravitational field and comparing it to an electrical field, and we pointed out that the potential energy difference when moving a charge, okay, from voltage 1 to voltage 2, okay, was related to the difference between the voltages times the charge, okay, and it was, the point to remember was that the energy was related to the difference between the voltages. Now, in the case of physics, as I pointed out, we work with charge and electric field. Here, the corresponding quantities will be current, which is the rate of flow of charge, dq by dt, and the voltage. Okay, and we have already seen how the voltage is related to the electric field. Now, moving on, so that kind of sets the stage for why we use voltages and currents. Now, the minute we know we are going to use voltages and currents, we start looking at what are called electrical elements. Okay, what is an electrical element? So you take a component or an element which has two terminals, okay, across which you can measure the potential difference and through which you can measure the current flowing. Okay, this would constitute an electrical element. So you would need a minimum to find out the voltage between two nodes or two terminals. You will need a minimum of a two-terminal element, right? And you can have more than two terminals also. You can have a three-terminal element, a four-terminal element, and so on. Okay. Can anybody give me an example of a three-terminal element? A transistor, right? You will learn more about a transistor in the analog circuits course. You will learn more about the transistor from the point of view of circuit design and analysis in the analog circuits course. If you want to know what goes on inside the transistor, you will learn more about that in the solid state devices course. Okay? Now, the way we will work with this is we will assume that in steady state there is no accumulation of charge inside the element. Okay? There is no accumulation of charge, so therefore the current going in has to be equal to the current coming out. Okay, based on charge conservation and no local accumulation of charge. Is that clear? So I in will be equal to I out. For this and across the terminals you have a voltage V. This is an example of a two-terminal element. Now, for any element you can establish a relationship between the voltage across the element, okay, across these two terminals, and the current through the element. Okay, you can express that the current as a function of the voltage or the voltage as a function of the current, whichever way is convenient. Okay, and similarly you can do the same thing for a three-terminal element or a four-terminal element and so on. Okay, the relationships will get more complex. Also, the relationship need not be linear. Okay, can anybody give me an example of a nonlinear element? A nonlinear two-terminal element? A diode. Okay, can anybody give me an example of a linear two-terminal element? A resistor. Okay, in today's class we will try to look at this, okay, because this will be pertinent as we go forward about what linearity means. Now, somebody pointed out, when we can actually make these assumptions. There are two things to note about, when we deal with voltages and currents in steady state and so on, and when we try to apply these, principles of conservation of charge and so on, you actually end up with two laws, right, which are Kirchhoff's voltage law and Kirchhoff's current law. We looked at these last class. But the point to remember is unlike in physics, we do not assume in a spatial distribution of charge, for example. Okay. Number two, we actually look at aggregate quantities. Okay. We do not look at distributed quantities. So Kirchhoff's laws, for example, may be violated in certain cases, but we will not consider those cases in this course. Okay. As far as we are concerned in this course, KCL and KVL are always valid in this course. Okay. Of course, there are certain cases, as we pointed out last time, for very large systems, okay, at very high frequencies, this is not valid. So the speed of the system matters, the size of the system matters. Okay, which is why I pointed out that these are very localized small scale systems which we will assume in this course. What are these laws? KVL and KCL. So to understand those, we need to define what an electrical circuit is. Okay, an electrical circuit is an interconnection of two or more elements, but there is a small caveat to this. What was that? We looked at it in last class, but we didn't write it down as part of the definition. What is that? Can it just be a simple interconnection of two or more elements? Can this be would this be an electrical circuit? As I pointed out, this, okay, you could say it's an electrical circuit, but it's a trivial electrical circuit where there is nothing to analyze. Why is that? There is no current flowing through this very clearly, because you can apply principle of conservation of charge in case there is any current flowing. You can apply it to these N terminals and you can show that there is no current flowing. Right? Current flowing out of the device has to be current flowing into the device. Okay? So this is really not a trivial, this is really not a relevant circuit in most cases, and we don't want to include something like this in the definition of a circuit. So how can we define it? How can we modify our definition? Interconnection of two or more elements that form at least one loop. Okay? Okay, it's an interconnection of two or more elements that form at least one loop. And we also looked at this very particular example here. Okay, so we drew it like this, and then we said we have to complete the loop for this to be a meaningful circuit. Okay. For the electrical circuit, we can define two characteristics. Okay. One is what is called a node, which is the point of connection between two terminals of different elements. So I take the terminals of two elements, I connect them together at a single point, that's called a node. It can be two or more elements. We also looked at that example. You can connect three of them at the same point, that is also a node. So it's two or more elements at the same point. Okay. Similarly, a loop, you can define that as starting from a particular node, any node. Okay, you traverse through the circuit, and if you are able to end back at the same node, that is called a loop. Okay, through the circuit. So the circuit topology must allow you to start from a particular node and end back at the same node. There may be multiple paths, which means you have multiple loops. This is an example of a circuit which has a single loop. We also looked at the example of a circuit which has three loops. Okay, so this circuit has one loop like this, second loop like this, third loop like this. Okay, you can. I just started off from the top left side node. You can start from any node. So what does Kirchhoff's voltage law tell you? As we saw last time, the potential difference between 2 points, okay, is just defined independent of other points in the circuit. Okay. So what that means is, if I start from node 1, okay, and come back to node 1, the potential difference between that has to be 0. Okay. So if I start off from, so because the potential of a particular point is a characteristic of that point, if I go through the circuit and come back at the same point, that has to be 0. Therefore, Kirchhoff's voltage law can be defined in this form. The sum of the voltages around the loop will be 0. Okay. This is how you would define Kirchhoff's voltage law. Similarly, at any node, okay, assuming no local, accumulation of charge, you can show that the current coming in has to be equal to current leaving out, okay, out of the node, or you can express it in a different way. the sum of all currents entering a node has to be equal to 0 because there is no charge accumulated over time. Is that clear? So this is an expression of Kirchhoff's current law. It can be expressed in many ways, right? This is the most common way of expressing it. You can say sum of all currents entering a node should be equal to sum of all currents leaving a node. All of this depends on the convention you have chosen for the directions of the currents. As I pointed out, we can choose the current in this way. I think we pointed that out later. If you take any particular element, quite often we might choose the voltages and currents in this fashion. We could choose the voltage in this fashion, but the current in the opposite fashion, okay? Except the sign of the current will be minus I, okay? Or you could choose the sign of the voltage in the other side also, and that voltage will be the negative of the voltage chosen in the first case. So this is just a convention. The potential difference between nodes A and B may be 2 volts. The potential difference between nodes B and A would be minus 2 volts. Okay, it's a potential difference you are talking about. Okay. Now similarly, if I actually choose an n-terminal element, okay, if you choose an n-terminal element, how many independent voltages and currents can you choose? Can you actually define for the system? There are n-1 independent voltages and n-1 independent currents. Okay, how do you know this? Because a voltage is always defined with respect to a reference. Okay, you could take any one of those n nodes as the reference and define the voltages of everything else with respect to that. Okay, similarly, the sum of all currents entering a particular element also has to be 0. Okay, because you don't expect charge to accumulate in an element. Okay, so sum of all currents entering also has to be 0, which means there are only n-1 independent currents. Is that clear? Any questions on this? Okay. Similarly, if you have, this is for an n-terminal element. Similarly, if you have a network, an electrical circuit, okay, which has some n nodes and m loops, you can show that some of them will be dependent on the other. Okay. Note that I did not say n-1 or m-1 because that really depends on the topology of the electrical circuit inside. Okay. But there will be some number of independent voltage and current variables. Then we started looking at several of these two-terminal elements. Okay, so the first one we looked at was a resistor. This is very well known. The voltage is related to the current in a linear fashion, V equals IR, okay, or I equals G times V. If you had to plot the dependence, okay, you would plot it, let's say I versus V. It would be a linear behavior with a slope of G. This is 1 by R. The unit of resistance is ohm. Okay. You also have capacitors which are related. The current and voltage are related in this fashion. For a capacitor, I is C dV by dt. For an inductor, V is L di by dt. Okay. We also looked at two other systems, two other electrical elements. One is the voltage source, okay, which also I will add, again I'll add a small qualifier here, okay, because of what we are going to study in today's class. I'll call it an independent voltage source, okay. This particular symbol stands for an independent voltage source. An ideal voltage source, an ideal independent voltage source is that which is able to maintain the voltage across it independent or regardless of the current that flows through it. Okay, if I take an ideal 10 volt voltage source, okay, it doesn't matter whether I draw 1 milliamp, 1 ampere, 1000 amperes, it does not matter. it will always maintain a potential difference of 10 volts across it. Okay, that is the definition of an ideal voltage source. Similarly, I can define an independent current source, okay, which is defined as an element that maintains a current I naught. In this case, I take a current source of value I naught. It maintains a current I naught in the direction shown from terminal 2 to terminal 1, irrespective of the voltage across it. Okay, so it does not matter if I have a voltage of 0 volts, 1 volt, 10 volt, minus 100 volts, minus 1000 volts, it does not matter. It will maintain a current I naught from terminal 2 to terminal 1. Okay, this is the property of this particular element. Okay, and of course the characteristic is pretty obvious. Now before we go further, I just wanted to discuss a couple of properties of electrical elements. The first one we are interested in will be linearity. Any idea what defines the linearity of an electrical element? Anybody? When can you say an electrical element is linear? Anybody? Is a resistor a linear element? All of you said yes. Why? The voltages and currents are related linearly. Okay, that's a good place to start. Unfortunately, that is not all there is to it. So, VI the VI relationship is linear. Okay, so that is a good place to start, but that is not all there is to it. Any other property we might be interested in? You might have learned this in mathematics. When is a function called a linear function? You might have learned this in linear algebra at some point of time. There are two properties we are interested in. What is that? If I have a function f of x, okay, when will I call it linear? If I have a function f of x, right, if I look at f of x plus y, that should be equal to f of x plus f of y, right? That is one condition for the function to be linear. What is the other function? What is the other relationship? This is called the additive principle. What is the second one? So the second one is, if I take a constant a, okay, real number a, f of ax needs to be equal to a times f of x. Okay. This is called homogeneity. Okay. Together, these two relationships put together result in a particular name. A particular name is given to these two sets of relationships. What is this? Together. What is that? Any idea? It's called superposition. Any of you have heard of the superposition principle? You've heard of this? Okay. So it is not just that the V2I relationship is linear. More specifically, you should be able to apply superposition. Okay. In other words, what I mean is, let us say the voltage was a certain V equals f of I, right? So if I take I1, I get a voltage V1. I have a current I2. I have a voltage V2 across the element. Then V1 plus V2 should be f of I1 plus I2. That is what this says. Okay. Similarly, if I have a current I1 flowing through this, which has thereby developing a voltage V1 across the terminals, if I have A times, some 5 times I1 or 10 times I1, I need to have 5 times V1 or 10 times V1 voltage developed across the element. Is that clear? So this very clearly establishes the linearity of an element. So for the resistor V equals IR, okay, do you think superposition is applicable for this resistor? Is it? It is, right? So this is a linear element. What about a capacitor or an inductor? Are these linear elements? So in other words, is the differential operator a linear operator? It is. Okay. You can apply the superposition principle, both principles, and confirm it for yourself. So both the inductor and the capacitor are also linear elements. What about a voltage source? V0. Is it a linear element? You will find that it's not. Okay, you apply this principle, you will very easily find that it's not. The same thing with a current source too. These are not linear. Okay. If you go back to the characteristic we drew, for example, for the current source, this is very obviously a straight line. It is not that this is not a straight line, right? So just imagining the voltage current relationship to be a straight line does not automatically say that the element is linear. Is that clear? If you look at the characteristics of both the voltage source and the current source, okay, the relationship is linear, okay, or rather the plot that you draw is a straight line. But it is not a linear element because it does not satisfy superposition. Okay, that's a very important thing to remember. Let us say I have a fictitious element, okay, which has a characteristic like this. This is the IV curve. Is this a linear element? No. Why not? Exactly. Right? It's very clear that this has the form AX plus B. Okay? That B term, the constant term, okay, does not lend itself to the superposition principle. Okay? So if you have a straight line, it has to pass through the origin. Okay? In fact, this kind of relationship, this kind of function is truly not a linear function. It is what is called an affine. Okay? It is called an affine function. Okay? It is a straight line which does not pass through the origin. Okay? So superposition principle is not applicable. Okay? So that is as far as linearity goes. So now you will be able to tell, right? If you want to test whether a system, an element is linear or not, all you have to do is apply superposition. So of course, if you have a relationship V equal to I times K times I, that's linear, it passes through the origin. You know that the derivative function is a linear function. Now there are a few other functions, it may not be so obvious to you, but there are a few other functions which are linear. I don't know, can anybody think of any other function that might be a linear function? Obviously anything with a quadratic or a thing will not satisfy this. Okay, a higher polynomial will not satisfy this. Okay, any other operator, mathematical operator or function that might satisfy linearity? Obviously once the derivative is there, is the integral valid? Just think about it. Remember that the integral has two forms, the indefinite integral and the definite integral. Okay, think about whether both of these are linear or not. Okay, but there are other functions, just take it from me. You can go and do the homework if you want to find out which other functions are linear. Okay, so but I'll take the example of an inductor again to define a second property. So let us just take the relationship between the current and the voltage is V equals L di by dt. Okay. Now for all the other elements, for the first few elements which we, resistors, sources and so on, we drew the curve. Can you actually draw the VI curve for this particular IV curve for this particular element, or for a capacitor for that matter? Can you draw the voltage current characteristics, okay, for a capacitor or an inductor at any time, right? Obviously now the voltage and current are time dependent. Okay, in the original case, if you take the case of a resistor, okay, let's say the resistor value was constant, you apply a constant voltage, the current is also constant. Obviously in this case the current or voltage may be time varying, but at any instant of time, can I draw the V to I relationship for an inductor or a capacitor? So as it may not be so obvious from this expression, but if you actually write out the inverse relationship, okay, expressing the current as a function of the voltage, what is that? That is actually an integral relationship, right? What does an integral relationship mean? Okay, that's okay. That is the basic definition of an integral. But what that means is, so if you actually I, okay, is 1 by L V dt, right? This is the integral relationship. What about the limits of the integral? If you at any time t, okay, if you want to find out the current through an inductor, you will have to know the past history of the voltage. Okay, in other words, this is an element with memory. Okay, the instantaneous voltage current relationship depends on the past values of voltages and currents. Okay, in this particular case, the I of t, okay, not only depends on V of t, but it also depends on all the past values of t. Okay, so in other words, they are elements with what is called memory. Okay, so only if I know the past values, I can actually know the exact value. Without knowing that, I cannot draw out the relationship. Okay. Now, the other kinds of sources, there are two other kinds of elements that we are interested in. So, the first of them is what I call control sources. Okay. So far we have been seeing independent sources, independent voltage sources and independent current sources. Okay. However, there is also a class of sources which are dependent sources or controlled sources. We'll start off with the simplest possible example. Let us assume that it's a voltage source. Okay. The symbol of a of a control source, okay, is usually represented with a rectangle. Sorry, with a with a rhombus kind of, with a diamond shape, shall we say? Okay. So, and you put in two more lines here, okay, to show, to denote the quantity that is controlling this particular element. Okay. So very specifically, I have put in a voltage at the output. Okay. I'll call that the output quantity V0. Okay. In this particular case, I am going to show it being controlled by an input voltage Vi. Okay. So what kind of element is this? This element is called a voltage controlled voltage source. Okay. Very often abbreviated as VCVS. Okay, it's much easier to keep saying VCVS instead of saying voltage controlled voltage source. Very clearly, the controlling variable is a voltage. Okay, the controlled variable is also a voltage. Okay, what is the relationship between VO and VI? VO will be some K times VI. Okay, this is the relationship. Okay, I apply a certain voltage here, I get K times the voltage there. What are the units of K? K has no units, right? It's voltage by voltage. Okay, this is the kind of relationship you get. Now note that we are not saying anything about K right now. Its unit, it has no units, but it could be time varying, for example. Okay, so I am not saying anything about K. Now why are we interested in these kinds of systems? Control sources. Any idea? So what you will find is in future courses in circuit design, you will find these to be practically everywhere. Okay, if you in a couple of semesters you will be doing the analog circuits course. Okay, you will find that you will find people throwing in voltage control, voltage source. I mean controlled sources all over the place. Okay, there's a reason why we study these also. And remember that this is a 4-terminal element, the way I have shown it, but it can be a 3-terminal element also. It does not, so let me name these as A, B, C, D. I have shown it as a 4-terminal element, but for example, it does not need to be. B and D, for example, could be a common terminal. Okay, that would give you a 3-terminal controlled source. Okay, or A and D could be common and so on. Okay, you can have different possibilities also. This is the most general case. Okay, so this is a voltage controlled voltage source. How many different kinds of control sources can you have now? You can have 4 different kinds of control sources. Okay, you can have VI and VI, so you can have this relationship. Okay, you can have this too. Okay, so we will quickly look at all of these. Let us look at the voltage controlled current source. Okay, the controlling variable is a voltage. Okay, the output is a current source. So note that the controlled source is placed inside a diamond as a diamond. If it's a voltage source, you show it as a voltage source. If it's a current source, you put an arrow through it to show it's a current source. And obviously the output variable is a current. Okay, input variable is a voltage. I0 is some G times VE. Why have I called it this constant G? Because the units of this particular variable is that of conductance. Okay, 1 over resistance. Okay, this is a voltage controlled current source. Similarly, a current controlled voltage source. The representation at the input is slightly different. Now the input controlling variable is a current, therefore you are going to show a short between the input terminals. In other words, you are going to pick up a wire through which a certain current is flowing, an ideal wire, and use that as the controlling variable, and that is what is shown here. So that is II. This is a current controlled voltage source, VO. PO is sum R times II. Maybe I should be a little bit more. I'll use GC and RC to show that the controlling variable, proportionality of constant of the controlling. So this is as the, okay, has the units of resistance. And finally, did everybody get this? The current controlled voltage source. Finally, you also have the current controlled current source. Okay, for brevity, it's used, it's denoted by CCCS. I have an input controlling variable which is a current. And an output variable which is a voltage, some I naught to some K times II. Is that clear? Okay, so you can have 4 types of control sources. Okay, voltage controlled voltage source, voltage controlled current source, current controlled voltage source, and current controlled current sources. And obviously these can also be part of an electrical network, okay, or an electrical circuit. Okay, we looked at the simplest case of making the electrical circuit with 2 terminal elements, but these are obviously 4 terminal elements. They can also be part of the electrical circuit. Okay. Now actually one other point, if you look at the elements we have seen so far, I'll use the resistor as the simplest element. Okay, I have a VI relationship which is V equals IR, right? That is the VI relationship. What does that mean? I take this resistor, I apply a voltage V. Okay, I take an ideal voltage source, connect it across the resistor. A current of V by R will flow through this resistor. Okay. If I take a current source of value V by R, okay, and pump it through the same resistor, a voltage V will be developed across it. Okay. So in other words, okay, this VI relationship can be seen as V equals IR or I equals V by R. Right? This can be seen either way, both mathematically as well as physically. Physically, because I can take the same resistor and force the current through the resistor and develop a voltage, or apply a voltage across the resistor and force the current to flow through it. Okay? Apply a voltage and cause the current to flow through it. So in other words, mathematically the relationship is valid, obviously, always, but Even physically this is valid because the connection can always be made with a voltage or a current. So in other words, the cause-effect relationship is also bidirectional. Okay. The thing to remember is that for a controlled source, I'll take the example of a VCVS. Okay, but this is valid for any controlled source. So let us say this was VI, VO, and let us say VO was some K times VI. Okay. Obviously, mathematically, this relationship can be written as VI equals VO by K. Okay. However, the cause-effect relationship is only in one direction. I have a voltage, apply a voltage VI here between A and B. Okay. I see a voltage K times VI across C and D. Okay. I cannot apply K times VI across C and D and expect a voltage VI at the input. Okay. Okay. The cause is VAB and the effect is VCD. Okay, not the other way around. This kind of element is what is called a unilateral element. Okay, because the cause-effect relationship goes only in one direction. Okay, this is what is called a unilateral element. Is that clear? Any questions? So whenever you use the control source in the future, okay, now or in the future, remember that it is always from controlling variable to the control variable, not the other way around. Now, when you do the analysis, writing VI equals VO by K may be easier when you are doing analysis. Okay, but if you actually take a control source and try to apply K times, K times VI at the output, you will not get VI at the input. Okay, that is the point. For example, if I tell you I take a voltage controlled voltage source, I observe at the K value is 10, I observe a voltage of 10 volts across C and D. What is the input voltage? Right? This is the problem of analysis. Of course, you know that only if you apply, VO by K, you will get a voltage of VO at the output. Okay? Does not mean that the cause-effect relationship is backwards. Okay? I observe a voltage of 10 volts. What is the input? It's 1 volt if K is 10. Okay? So that's one type of, 4-terminal element, which is a controlled source. Now the other type of element that we are going to look at, I think we have a couple of 2-3 minutes left in the class, is we'll start it off. It's called a what is called a mutual inductor. Has anybody heard about this kind of element? Mutual inductor? How many of you have heard about this? Okay, a decent number. Okay, fine. So mutual inductor also happens to be a 4-terminal element. Okay. This also happens to be a 4-terminal element and it's drawn in this way for convenience. Okay. Now I have two sets of voltages and currents between the input terminals and between the output terminals. So I'll call those V1, I1 and V2 and I2. Okay. Now, actually, before we go further, I had a question. Maybe we'll just spend a couple of minutes discussing that. I don't know if you noticed, but in all the circuits that I drew, for all the elements that I drew, okay, I chose the voltage and current directions in this form. I told you it's just a matter of convention. Okay? I told you it's just a matter of convention. You can choose the current in the opposite way also. It will just turn out to be negative. Okay? But there is a specific reason for choosing it this way. Right? I am sure you have seen this before. When you draw a resistor, okay, you always represent the voltage and currents in a very specific manner. Right? If you set the signs of the voltage as plus and minus, the current always flows into the resistor, into the positive terminal of the resistor. Right? And current leaves the negative terminal of the resistor. Any idea why that is? Why do you choose this convention? Yes? No, but I said it's just a matter of convention. You're right. I can look at the same current as a negative current flowing from in the other direction. So it's a matter of convention. That is right. You're right. Current will flow a positive current will flow from higher potential to lower potential. Right? I'm talking about the convention. So this is what is called if I give the name, you might get some idea as to. This is the passive sign convention. Okay. Does anybody know what passivity means? What is passive with respect to electrical circuits? Okay, so anyways, just take it for now. We will, in a few classes, we'll soon find out what passivity means. Okay, what we mean by a passive element. Okay, the opposite of this is an active element. Okay, but you will find that this is the passive sign convention. Okay, which is the most common convention followed. So in tomorrow's class, we'll continue with this. We'll continue with the mutual inductor and look at, what the characteristics of a mutual inductance is.